Welcome followers. Today's video is about detail of primary and secondary aircraft control surfaces. Stay tuned. An aircraft control surface refers to the aerodynamic components on an aircraft used to manage its attitude and orientation by controlling its roll, pitch, and yaw. These surfaces are movable parts, such as flaps and rudders that are manipulated by the pilot through control systems, allowing for precise maneuverability and stability in various flight phases. Flight control systems. Aircraft flight control systems classified as primary and secondary. Primary control system. These are ailerons, elevator or stabilator, and rudder, required to control an aircraft safely during flight. The secondary control system. These surfaces enhance the effectiveness of the primary control surfaces or adjust the aircraft's aerodynamic profile for optimal performance. These includes wing flaps, leading edge devices or slat, spoilers, and trim systems. We will discuss more on these later. Flight control systems and characteristics can vary greatly depending on the type of aircraft flown. The most basic flight control system designs are mechanical and date back to early aircraft. They operate with a collection of mechanical parts, such as rods, cables, pulleys, and sometimes chains to transmit the forces of the flight deck controls to the control surfaces. Mechanical flight control systems are still used today in small general and sport category aircraft where the aerodynamic forces are not excessive. As aviation matured and aircraft designers learned more about aerodynamics, the industry produced larger and faster aircraft. Therefore, the aerodynamic forces acting upon the control surfaces increased exponentially. To make the control force required by pilots manageable, aircraft engineers designed more complex systems. At first, hydromechanical designs, consisting of a mechanical circuit and a hydraulic circuit, were used to reduce the complexity, weight, and limitations of mechanical flight control systems. As aircraft became more sophisticated, the control surfaces were actuated by electric motors, digital computers, or fiber optic cables. Called fly-by-wire, this flight control system replaces the physical connection between pilot controls and the flight control surfaces with an electrical interface. In addition, in some large and fast aircraft, controls are boosted by hydraulically or electrically actuated systems. In both the fly-by-wire and boosted controls, the feel of the control reaction is fed back to the pilot by simulated means. Current research at the National Aeronautics and Space Administration (NASA) involves Intelligent Flight Control Systems (IFCS). Now, let's get back to classification. Primary control system. Aircraft control systems are carefully designed to provide adequate responsiveness to control inputs while allowing a natural feel. At low airspeeds, the controls usually feel soft and sluggish, and the aircraft responds slowly to control applications. At higher airspeeds, the controls become increasingly firm and aircraft response is more rapid. Movement of any of the three primary flight control surfaces, ailerons, elevator or stabilator, and rudder, changes the airflow and pressure distribution over and around the airfoil. These changes affect the lift and drag produced by the airfoil or control surface combination, and allow a pilot to control the aircraft about its three axes of rotation. Ailerons. Ailerons control roll about the longitudinal axis. The ailerons are attached to the outboard trailing edge of each wing and move in the opposite direction from each other. Ailerons are connected by cables, bell cranks, pulleys, and/or push-pull tubes to a control wheel or control stick. Moving the control wheel or control stick to the right causes the right aileron to deflect upward and the left aileron to deflect downward. The upward deflection of the right aileron decreases the camber, resulting in decreased lift on the right wing. The corresponding downward deflection of the left aileron increases the camber, resulting in increased lift on the left wing. Thus, the increased lift on the left wing and the decreased lift on the right wing causes the aircraft to roll to the right along longitudinal axis. Since the downward deflected aileron produces more lift as evidenced by the wing raising, it also produces more drag. This added drag causes the wing to slow down slightly. This results in the aircraft yawing, which is called adverse yaw toward the wing, which had experienced an increase in lift and drag. The adverse yaw is a result of differential drag and the slight difference in the velocity of the left and right wings. Adverse yaw becomes more pronounced at low airspeeds. At these slower airspeeds, aerodynamic pressure on control surfaces are low, and larger control inputs are required to effectively maneuver the aircraft. As a result, the increase in aileron deflection causes an increase in adverse yaw. The yaw is especially evident in aircraft with long wingspans. To reduce the effects of adverse yaw, manufacturers have engineered 4 systems: differential ailerons, Fries-type ailerons, coupled ailerons, and rudder and flaperons. Differential ailerons. With differential ailerons, one aileron is raised a greater distance than the other aileron and is lowered for a given movement of the control wheel or control stick. This produces an increase in drag on the descending wing. The greater drag results from deflecting the up aileron on the descending wing to a greater angle than the down aileron on the rising wing. This slight increase in drag of the downward-going wing offsets the additional induced drag on the upward wing, helping to balance the resulting yawing moment. While adverse yaw is reduced, it is not eliminated completely. Fries-type ailerons. With a Fries-type aileron, when pressure is applied to the control wheel or control stick, the aileron that is being raised pivots on an offset hinge. This projects the leading edge of the aileron into the airflow and creates drag. It helps equalize the drag created by the lowered aileron on the opposite wing, and reduces adverse yaw. The Frise-type aileron also forms a slot so air flows smoothly over the lowered aileron, making it more effective at high angles of attack. Frise-type ailerons may also be designed to function differentially. Like the differential aileron, the Frise-type aileron does not eliminate adverse yaw entirely. Coordinated rudder application is still needed when ailerons are applied. Coupled ailerons and rudder. Coupled ailerons and rudder are linked controls. This is accomplished with rudder aileron interconnect springs, which help correct for aileron drag by automatically deflecting the rudder at the same time the ailerons are deflected. When the control wheel or control stick is moved to produce a left roll, the interconnect cable and spring pulls forward on the left rudder pedal just enough to prevent the nose of the aircraft from yawing to the right. The force applied to the rudder by the springs can be overridden if it becomes necessary to slip the aircraft. Flaperons. Flaperons combine both aspects of flaps and ailerons. In addition to controlling the bank angle of an aircraft like conventional ailerons, flaperons can be lowered together to function much the same as a dedicated set of flaps. The pilot retains separate controls for ailerons and flaps. A mixer is used to combine the separate pilot inputs into this single set of control surfaces called flaperons. Many designs that incorporate flaperons mount the control surfaces away from the wing to provide undisturbed airflow at high angles of attack and/or low airspeeds. The second primary control surface is elevator. The elevator is the primary control for changing the pitch attitude of an aircraft. The elevator controls pitch about the lateral axis. Like the ailerons on aircraft, the elevator is connected to the control column in the flight deck by a series of mechanical linkages. Aft movement of the control column deflects the trailing edge of the elevator surface up. This is usually referred to as the up elevator position. The up elevator position decreases the camber of the elevator and creates a downward aerodynamic force, which is greater than the normal tail-down force that exists in straight and level flight. The overall effect causes the tail of the aircraft to move down and the nose to pitch up. The pitching moment occurs about the center of gravity. The strength of the pitching moment is determined by the distance between the center of gravity and the horizontal tail surface, as well as by the aerodynamic effectiveness of the horizontal tail surface. Moving the control column forward has the opposite effect. In this case, elevator camber increases, creating more lift, less tail-down force, on the horizontal stabilizer. This moves the tail upward and pitches the nose down. Stability, power, thrust line, and the position of the horizontal tail surfaces on the empennage are factors in elevator effectiveness controlling pitch. The horizontal tail surfaces may be attached near to one of the following: lower part of the vertical stabilizer, at the midpoint or at the high point, as in the T-tail design. T-tail. In a T-tail configuration, the elevator is above most of the effects of downwash from the propeller, as well as airflow around the fuselage and/or wings during normal flight conditions. Operation of the elevators in this undisturbed air allows control movements that are consistent throughout most flight managements. T-tail designs have become popular on many light and large aircraft, especially those with aft fuselage-mounted engines, because the T-tail configuration removes the tail from the exhaust blast of the engines. An additional benefit is reduced noise and vibration inside the aircraft. In comparison with conventional tail aircraft, the elevator on a T-tail aircraft must be moved a greater distance to raise the nose a given amount when traveling at slow speeds. This is because the conventional tail aircraft has the downwash from the propeller pushing down on the tail to assist in raising the nose. The third primary control surface is rudder. Rudder is located on the trailing edge of the vertical stabilizer at the tail. The rudder controls movement of the aircraft about its vertical axis. This motion is called yaw. Like the other primary control surfaces, the rudder is a movable surface hinged to a fixed surface, in this case, to the vertical stabilizer or fin. It is used in coordinated turns, managing crosswind landings, and stabilizing the aircraft's directional movement. The rudder is controlled by the left and right rudder pedals. When the rudder is deflected into the airflow, a horizontal force is exerted in the opposite direction. By pushing the left pedal, the rudder moves left. This alters the airflow around the vertical stabilizer and creates a sideward lift that moves the tail to the right and yaws the nose of the airplane to the left. Rudder effectiveness increases with speed. Therefore, large deflections at low speeds and small deflections at high speeds may be required to provide the desired reaction. Application of the rudder is used to counteract adverse yaw. The amount of rudder control required is greatest at low airspeeds, high angles of attack, and with large aileron deflections. All turns are coordinated by use of ailerons, rudder, and elevator. Applying aileron pressure is necessary to place the aircraft in the desired angle of bank, while simultaneous application of rudder pressure is necessary to counteract the resultant adverse yaw. Secondary flight controls. Secondary flight control systems may consist of wing flaps, leading edge devices, spoilers, and trim systems. Flaps. Flaps are the most common high-lift devices used on aircraft. These surfaces, which are attached to the trailing edge of the wing, increase both lift, resulting in a nose-down pitching moment. The split flap is deflected from the lower surface of the airfoil and produces a slightly greater increase in lift than the plain flap. More drag is created because of the turbulent air pattern produced behind the airfoil. When fully extended, both plain and split flaps produce high drag with little additional lift. The most popular flap on aircraft today is the slotted flap. Slotted flaps increase the lift coefficient significantly more than plain or split flaps. On small aircraft, the hinge is located below the lower surface of the flap, and when the flap is lowered, a duct forms between the flap well in the wing and the leading edge of the flap. When the slotted flap is lowered, high-energy air from the lower surface is ducted to the flap's upper surface. The high-energy air from the slot accelerates the upper surface boundary layer and delays airflow separation, providing a higher coefficient of lift. Thus, the slotted flap produces much greater increases in maximum coefficient of lift than the plain or split flap. Fowler flaps are a type of slotted flap. This flap design not only changes the camber of the wing, it also increases the wing area. Instead of rotating down on a hinge, it slides backwards on tracks. In the first portion of its extension, it increases the drag very little, but increases the lift a great deal as it increases both the area and camber. Airfoil. The most common types are fixed slots, movable slats, leading edge flaps, and cuffs. Fixed slots direct airflow to the upper wing surface and delay airflow separation at higher angles of attack. The slot does not increase the wing camber, but allows a higher maximum coefficient of friction because the stall is delayed until the wing reaches a greater angle of attack. Movable slats consist of leading edge segments that move on tracks. At low angles of attack, each slat is held flush against the wing's leading edge by the high pressure that forms at the wing's leading edge. As the angle of attack increases, the high pressure area moves aft below the lower surface of the wing, allowing the slats to move forward. Leading edge flaps, like trailing edge flaps, are used to increase both coefficient of lift and the camber of the wings. A small increment of leading edge flaps increases lift to a much greater extent than drag. As flaps are extended, drag increases at a greater rate than lift. Leading edge cuffs, like leading edge flaps and trailing edge flaps, are used to increase both coefficient of friction and the camber of the wings. Unlike leading edge flaps and trailing edge flaps, leading edge cuffs are fixed aerodynamic devices. In most cases, leading edge cuffs extend the leading edge down and forward. This causes the airflow to attach better to the upper surface of the wing at higher angles of attack, thus lowering an aircraft's stall speed. The fixed nature of leading edge cuffs extracts a penalty in maximum cruise airspeed, but recent advances in design and technology have reduced this penalty. Spoilers. Found on some fixed-wing aircraft, high-drag devices called spoilers are deployed from the wings to spoil the smooth airflow, reducing lift and increasing drag. Spoilers reduce lift and increase drag during descent and landing. On gliders, spoilers are most often used to control rate of descent for accurate landings. On other aircraft, spoilers are often used for roll control, an advantage of which is the elimination of adverse yaw. To turn right, for example, the spoiler on the right wing is raised, destroying some of the lift and creating more drag on the right. The right wing drops, and the aircraft banks and yaws to the right. Deploying spoilers on both wings at the same time allows the aircraft to descend without gaining speed. Spoilers are also deployed to help reduce ground roll after landing. Trim systems. Although an aircraft can be operated throughout a wide range of attitudes, airspeeds and power settings, it can be designed to fly hands-off within only a very limited combination of these variables. Trim systems are used to relieve the pilot of the need to maintain constant pressure on the flight controls, designed to help minimize a pilot's workload. Common types of trim systems include trim tabs, balance tabs, anti-servo tabs, ground adjustable tabs, and an adjustable stabilizer. Trim tabs. The most common installation on small aircraft is a single trim tab attached to the trailing edge of the elevator. Most trim tabs are manually operated by a small, vertically mounted control wheel. Placing the trim control in the full nose-down position moves the trim tab to its full-up position. With the trim tab up and into the airstream, the airflow over the horizontal tail surface tends to force the trailing edge of the elevator down. This causes the tail of the aircraft to move up and the nose to move down. The movement of the elevator is opposite to the direction of movement of the elevator trim tab. Balance tabs. The control forces may be excessively high in some aircraft, and in order to decrease them, the manufacturer may use balance tabs. They look like trim tabs and are hinged in approximately the same places as trim tabs. The essential difference between the two is that the balancing tab is coupled to the control surface rod so that when the primary control surface is moved in any direction, the tab automatically moves in the opposite direction. The airflow striking the tab counterbalances some of the air pressure against the primary control surface and enables the pilot to move the control more easily and hold the control surface in position. Servo tabs. Servo tabs are very similar in operation and appearance to the trim tabs previously discussed. A servo tab is a small portion of a flight control surface that deploys in such a way that it helps to move the entire flight control surface in the direction that the pilot wishes it to go. A servo tab is a dynamic device that deploys to decrease the pilot's workload and destabilize the aircraft. Anti-servo tabs. Anti-servo tabs work in the same manner as balance tabs except, instead of moving in the opposite direction, they move in the same direction as the trailing edge of the stabilator. In addition to decreasing the sensitivity of the stabilator, an anti-servo tab also functions as a trim device to relieve control pressure and maintain the stabilator in the desired position. Ground adjustable tabs. Many small aircraft have a non-movable metal trim tab on the rudder. This tab is bent in one direction or the other while on the ground to apply a trim force to the rudder. The correct displacement is determined by trial and error. Usually, small adjustments are necessary until the aircraft no longer skids left or right during normal cruising flight. A ground adjustable tab is used on the rudder of many small airplanes to correct for a tendency to fly with the fuselage slightly misaligned with the relative wind. Adjustable stabilizer. Rather than using a movable tab on the trailing edge of the elevator, some aircraft have an adjustable stabilizer. With this arrangement, linkages pivot the horizontal stabilizer about its rear spar. This is accomplished by the use of a jack screw mounted on the leading edge of the stabilator. Followers, do you know how military jets have significantly higher maneuverability than commercial airplanes? This is possible due to aerodynamic design and shape, high thrust-to-weight ratio, Advanced control surfaces and canards. Lightweight and sturdy materials. Fly-by-wire, FBW, and computer-aided stability. Compact and agile for combat tactics. Generally, flight control surfaces are movable parts on an aircraft's wings, tail, and body that control its movement and stability. Please like, share, subscribe. Thank you for watching.